Right, welcome everyone. This week we're happy to welcome Velimir Illic from the Mathematical Institute of the Serbian Academy of Sciences and Arts, and we'll be hearing about some generalized information measures. So please go ahead, Velimir.
Okay, hello all. First of all, thank you very much for inviting me for this seminar series. I really like this deep seminar, and it is great honor and pleasure for me to take a part of this. So, as you announced, today's talk will be about generalized information measures. I put it like an overview and characterization. By an overview, I mean to present you not all, but majority of generalized information measures, particularly generalized entropies that were considered before in statistical physics and information theory. And by characterization, I mean setting up the axioms for quantification of these measures and for establishment of their uniqueness. And I always like to start the presentations of this kind with this short table, which give a very nice look into the development of the field. So just to check, you see now the slide generalized entropies overview, right?
Yes.
Okay, thank you. So here I put in the table some names. For any of these names, we have one information measure, and I separated the table in two parts, left and right part. Uh, and why is it so? So left side are mostly people from information theory and mathematics, and on the right hand side, mostly people from statistical physics. And it was how the development of field went on. So it started after Boltzmann and Gibbs, of course, but from information theory point of view, it started with Shannon. And somewhere 61st, Rini introduced a generalization, one parameter generalization of Shannon entropy. And after Rini, we had a lot of researchers that considered Rini's generalization and were introducing another generalizations of Shannon entropy, and they were primarily concerned with their mathematical properties from one side and from information theoretical properties from another side. And then this series of new entropies lasted till somewhere 80s. Then there was some period of pause in the research until Konstantinos Salis renewed the topic and established a new kind of statistical mechanics based on redefinition of the entropy. Essentially, what he did, he took this Haverda-Charvat entropy as a basis for thermodynamics instead of Boltzmann-Gibbs one. So just maybe it would be more convenient if I put full screen. Okay. Okay, and after Thalys, we had again series of researchers now from statistical physics that were analyzing the properties, thermodynamical properties of generalized entropies, as well as introducing additional generalizations. The meaning of generalization and the usefulness of generalization, not of all, but of some particular, will be shown later through the slides. And I would like to cover both of the aspects, both information theoretical and statistical mechanical aspects. And because of that, I separated this talk in four topics. The first one is pseudo-additive information content and pseudo-additive entropies, which will give us insight what is generalized entropy, then classification of generalized entropy using generalized Shannon-Kinchin axioms, one axiomatic approach which can help us to distinguish between different classes, generalized thermostatistics, so strongly pseudo-additive entropies, which will help us to understand the usefulness in statistical physics, and the last one, the alpha Q mutual information, the alpha Q capacities about applications in information theory, particularly in communication. Okay, so for the first one, what do we learn? I think everyone who learned information theory from standard text boxes started with this kind of interpretation of entropy, and entropy is an average information content. The information content, this is something which is related to an event. Entropy is something which is related to probability distribution or to random variable. And when we are creating information content, it is the measure of information carried by event. We assume that this function, information content, has to satisfy certain properties, and here these properties are listed first at a qualitative level, like small changes in probability results in small changes in information content value. We can translate it immediately to continuity of this function when we want to write down it. Then the higher probability, the lower information carried by event. This is actually a bigger surprise, bigger information. This is the idea. Then information content is additive. This one is critical. We will come back later to this and normalize this information content of probability of event with 1.5 has unity measure. So this is just to fix constants. And this additivity means that if we receive information from different sources, we want to somehow compose the information, and we say, okay, I pick up a part of information from this side, a part of information from that side, and the total information is the kind of sum of these two informations. We can use, in simplest case, we can use this ordinary plus, but how are we adding information in our brain? We don't have a clear answer. Very likely we will not have it. But ordinary plus is the simplest choice for this. And then if we take this ordinary plus, we will get this kind of functional equation, and all of these additional assumptions will help us to transform it easily to Cauchy functional equation and to come with a unique solution for information content, which is minus log p. This log will be used like logarithm with the base 2, since we are doing with Hartley, so that we have information carried by one bit to be 1. In statistical physics, natural logarithm is usually used, but I hope that we will not come to the confusion during the presentation. We can also here go with natural logarithm, then we will measure information in other units, but for now let us go with log 2. Okay, so as I mentioned, ordinary plus is just a simplest case, and we can consider even more general operations, and one of these is pseudo addition, which is generated using this so-called generating function eta. This one is increasing and differentiable. These two properties are more, the second one is more technical, but the function to be increasing is actually to follow this. The higher the probability, the lower the information carried by the content. So we want to form generalized information content as an increasing information of additive information content. And this is actually the definition of a generalized logarithm. So generalized logarithm is an increasing function of usual standard logarithm. Or we can say generalized logarithm is just an increasing function of x here, or decreasing function of event probability. And if we define information content using the generalized logarithm, we will get that it is pseudo-additive following this pseudo-additivity rule. And here is one particular case of generalized information content in generalized logarithm, which is so-called Q logarithm and Q additive information content. These are bases for Thales entropy and related ones. And here is the pseudo-additivity rule. We will see here this ln2 participating in the expressions. This is exactly to manage this log2 ln2 passage. And here, when we go to generating map, we can observe it by putting the limit q tends to 1. We will come to the case of x, which is actually the case of additive information content, additive logarithm, and standard addition. Another example, kappa additive information content. Again, we can form it in the same way. Small difference in generating function, we can compare it. So in kappa, we, instead of -1 in the denominator, we have again 2 to the minus kappa x. But this will give us different pseudo-additivity rule, and this is the rule with this sign hyperbolic and its inverse. We can define Q logarithm in the same manner, and this is the basis of Kaniadakis entropy and its generalization. Maybe it is at least interesting to mention relationship of this pseudo-additivity rule with special relativity, although I'm mentioning it purely at mathematical level. So if we are given one-dimensional frame S prime that is moving with constant speed to the one-dimensional frame S, I put it S prime going to the left to the S, and we are given two identical particles of the rest mass m. Particles are A and B. We can compute relativistic momentum using this formula. On the left side, we have the velocity addition rule. So if we are in frame S, I is moving toward right with the velocity v1, B toward left velocity v2, but in the frame S prime, B is not moving, 0. It is the same as the velocity of the frame with respect to S, and I is moving towards right in accordance to this velocity addition rule. And on the other side, if we compute corresponding momentums, we will obtain that momentum of B with respect to frame S prime is 0, but momentum of A could be obtained as kappa kappa sum of these two momentas. And it was actually the main motivation for Kaniadakis to establish his measure. And yes, we will see here that actually these two lead us to different parts in different measures in different research fields. This dependence of pseudo-additivity rule which is chosen, which is very often made just for the matter of mathematical beauty, but at the end, very, very big communities working on approving these alternative theories. So here is down bottom of the slide, I provided a map which is showing the relationships between different entropies that we are going to pass through now. So in the bottom line, we have Shannon entropy, then go up, we have three generalizations, Tsalis, Rini, and Kaniadakis, then level up Sharma, Mittal, and Sharma, Mittal, Tanea, and level up, I had to put it down because of space, but we have these final strong pseudo-additive entropies that were mentioned in introduction and trace form entropies. And what is common to all of these entropies is that they can be represented as an average information content. We mentioned that information content is a measure of information associated to an event, and we also mentioned that entropy is average of it. But what does it mean average? In the same manner as we don't know how are we adding information associated to an event, we also don't know how do we average the information. One particular choice might be this so-called linear average, or the average which is done using standard expectation operator, and we will obtain this if we put this f to be identity function. But we can also go with this so-called Kolmogorov-Nagumo average, which actually has all of nice properties as the standard average. Standardly defined mathematical expectation can be redefined in terms of Kolmogorov-Nagumo average, so that majority results of probability theory and statistics still hold. And this is the idea behind the usage of this kind of averages in information theory and statistical mechanics, and we are going to use it in order to form different kind of information measures. So what do we want to do now is to somehow classify these information measures to understand them better. And what is really interesting that they share a lot of common properties, and one of them is particularly important and distinguish between these two entropies, which is pseudo-additivity, or more precisely, strong pseudo-additivity. And now I will show what do I mean by that. So one way to introduce entropy might be in axiomatic manner, and this is done with so-called Shannon-Hinching axioms. And these axioms deal directly with the information of the event without any reference to information content. And here, what do we assume when we establish in axiomatical manner Shannon entropy? So first we say S is continuous function in probability. this is, I think, fair requirement for any function to be continuous so that we can deal with it. S takes its largest value for the uniform distribution. Yes, S is measured information, and if we have a lot of randomness, we expect to have a lot of information. If we have a lot of certainty, we do not expect to learn new information. Entropy is expandable. That means that if we extend the event space for zero measure probability event for zero probability event, then the total entropy will not change. And we have this is the critical and the most important property, this a strong additivity of Shannon entropy, which says that entropy can be decomposed in entropy of composed system AB can be decomposed entropy of first system plus conditional of entropy of the second system condition on the first one. Conditional entropy given here, again, we can proceed as before and think about different definitions of conditional entropy. Again, this is established like an average of so this S of B condition of AI is the uncertainty in system B if we know that something happened in system AI. And we are averaging over all of these uncertainties, and this average can also be changed. These weights in averaging can also be changed, and this is actually how are we classifying the map that we saw in previous slide. We will just change this axiom with another axioms, and we will come to all of the measures from the map. That's the idea. So we are replacing fourth Shannon-Kinchian axiom with another one, which will use pseudo-additivity and different kind of averages. And here I put also one more axiom. This will be just to fix additional constants, which will be normalization axiom. Let us start with the first modification. So you see here how do we define this conditional entropy. Difference with respect to Shannon conditional entropy is just this Q factor. So here instead of H, it should be TQ. So if we put Q equals 1, this axiom will be the same as fourth Shannon-Kinchian axiom. But now putting Q in the exponent of the weight and also adding this additional condition for fixing the constants, we obtain Thales entropy as the unique solution of the axiomatic system. And this is something which was done first by Haverda and Charvat in one form and later on rediscovered by Suyar in 2024. Okay, we touched Thales, so now we see also from the map, if we go with Q equals 1, we go to Shannon entropy. So let us now go further and go right up to Sharma-Mittal-Tanea entropy. Here, this decomposability rule is a bit complicated, and we also assume that entropy has particular form, which is the sum of the terms, so-called trace form, and we do also have the decomposition, the first line on the right. So if we put here, we can also consult map R equals kappa equals Q minus 1 over 2. We will actually R equals kappa will cancel R and K, and this one will be actually the same as Salis, and this one will reduce to the entropy of the first system. And okay, it is not so intuitive pseudo-addition rule, but it is one way to characterize Sharma-Mittal entropy. And we can also go with R equals 0 to Kaniadakis case, and then we will come to this pseudo-additivity rule, and of course we can now put kappa equals 0 and recover standard Shannon case. Let us come back to Salis entropy once again. This is an alternative pseudo-additivity rule for Salis entropy. This time we are using a Q addition between entropy of system A and the conditional entropy. This is the first difference. In the previous axiomatic system, it was the ordinary addition. And the second difference is in the definition of the conditional entropy, which is this time defined in terms of these escort weights. And actually, we can think about entering any kind of pseudo-additivity rule, any kind of general Shannon-Khinchin axiom form here and try to discover the entropy form. But usually we will not be able to derive the unique class because, you know, this job is subtle, and there is not a lot of choices for this axiom, at least at mathematical, technical level, which allows us to derive the unique class. Okay, and this axiom was by Abe, and I came back to this because it will help me to visit the left side of the map, which is developed using this kind of thinking. So first, let us see Rini entropy, and now the difference between Rini and Salis entropy from the point of view of this axiom. In Rini case, we have ordinary addition and quasi-linear mean-defined conditional entropy. Go back to Salis. This is Q addition and trace form linear expectation. And here ordinary addition and quasi-linear expectation. And this will lead us to Rini entropy as unique solution, and this will lead us to an additive entropy. And Salis entropy is non-additive. Yes, it is Q additive, which is that it is not non-additive. Now we have their joint generalization, which is Sharma-Mittal entropy, which combines these two approaches. So it will use Q addition from one side, and from the other side it will use quasi-linear mean averages, and here is GSK4 for Sharma-Mittal entropy, and the form of Sharma-Mittal entropy is given in the table. Okay, we can now proceed even further. So if we recall from the first slide, we first introduced this general generating map as an increasing function. Then we specified, and using this general generating map, we defined pseudo-additivity operation. Then we specified this map to the map called HQ, which led us to the definition of Salis addition. So we can think here to go with more general pseudo addition instead of this Q addition, and it will bring us to the class of strongly pseudo-additive entropies, the class which can be represented as increasing transformation of Rene entropy. This class can also be approved from the point of view of statistical inference. There is another kind of axiomatic system due to Schur and Johnson, which can be shown that also quantify this class from the point of view of unique maximum entropy procedure in the presence of limited prior information. Okay, here are some examples of strongly pseudo-additive entropies. So now we passed through this map and came to the class of strongly pseudo-additive entropies. Now we can also think about another types of entropy that were not mentioned here. These are like more common and the most famous ones. And now I would like to show just a few examples of that belongs to this part of the map. One of them can be generated, so just put generating map to be x squared. It will be, I guess, the simplest possible choice for generating map. And then we will obtain the entropy, which is the square of Rene entropy. And this entropy will essentially have the pseudo-additivity rule, this x o plus y equals x plus y plus 2 square x square y. And this is actually the pseudo-additivity rule, which is followed by Beckstein-Hawking entropy, and this gives us nice analogy with black hole thermodynamics. So this is just to show that generalized entropies are not something strange, something not known. These are the measures that are used in different fields, although not called like that. And I also provide one more example that will be useful to show how can we apply generalized entropies, which is so-called super exponential entropy, which is defined in terms of Lambert function. Its pseudo-additivity rule is given in the bottom line. And here I would like to pass smoothly to generalized thermostatistics, and I would like to show on the example of super exponential entropy how can we use this generating map, how can it be useful, and how to recognize the usefulness of pseudo-additivity. And this is one interesting model called magnetic coins model. So if we imagine that we have n coins, we are measuring how many states we can generate with n coins. It will be 2 to the power of n standardly. And in this case, if we put all the states to be equally likely and we measure the entropy of the system, it will be standardly log number of possible states, and then it will go linearly with the number of coins with the system size. And here what is done by Jensen and his collaborators, that they set up an alternative model which introduces additional so-called sticky states or parity states. So during each trial, we can generate more than 2 to the power of n states, and in this case, the phase space has a super exponential growth given by this formula. And due to this super exponential growth, Rene entropy will not grow with n. Then immediately we cannot measure, for example, average Rene entropy with respect to the system size. And on the other side, if we can make a choice of h, which corresponds in this case to super exponential entropy, so that entropy grows linearly. So this function h is a kind of control function which help us to define extensive thermostatistics. By extensivity in this particular case, I mean linear growth of entropy, because now we are considering just a uniformly distributed system. In standard statistical physics, or at least from point of canonical ensemble, we will also take care about additional constraints such as internal energy, and then we will be led to maximum entropy distributions, which can go like Boltzmann-Gibbs if we use standard Boltzmann-Gibbs entropy combined with standard energy constraints, or we can get even more general distributions. And this is actually that we want to define this extensivity in canonical setups, and this is now the step to understand how can we use this function h in this case as well. So what is important when we are considering all of this from point of view of thermodynamics, it is that when we go to maximum entropy procedure and define the equilibrium distribution is a maximum distribution which is obtained by maximizing entropy subject to energy constraints. We can derive thermodynamics from the equilibrium entropy of equilibrium distribution, and by taking its Legendre structure. This is the basis of thermodynamics. So we define, we start from entropy and energy, we maximize, do this constrained optimization problem, and obtain probability distribution. And then for these quantities in equilibrium, we compute all other thermodynamic potentials, and we also define the temperature using entropy and energy in equilibrium. And what is here the point? That we do not need to use exclusively Boltzmann-Gibbs entropy or standardly defined energy if we want to obtain thermodynamics with well-behaved Legendre structure. So from the point of view of Legendre structure, we can take any function of entropy and any function of energy, okay, up to some technical conditions, and we can define the whole thermodynamics using an arbitrary functions. And here is just a sketch about relationship between different thermodynamics. One is defined in terms of Rene entropy, and another one is defined in terms of strongly pseudo-additive entropy. So one is Rene entropy, another one is transformation of Rene entropy. And now we want to see the effects of this pseudo-additivity and the effect of the generating map. So first, the effect on stationary distribution will not be observed, because if we maximize a function and we maximize its increasing transformation subject to the same constraint, we will obtain the same distribution. And the effects will be observed in the redefinition of the temperature. And this will induce later the asymptotical behavior of thermodynamical quantities. And here we can also play with the constraints. We can use different kind of constraints, as we mentioned before, that we use the escort weights instead of linear weights. Here is just to prove from thermodynamical point of view that we could also relate thermodynamics based on escort constraints, and based on linear constraints we can somehow put them equivalent. If we can come to this kind of diagram. So in the middle of this diagram we have a stationary distribution, which is in general for this framework Q Gaussian distribution, which reduces to Boltzmann-Gibbs one for special choice of parameter, and going from any of these definitions of thermodynamics, we can do the transformation to another one. So just as an example, upper left corner is a thermodynamics which is obtained by maximizing Rene entropy subject to linear standard energy constraints, and the right bottom corner is strongly pseudo-additive entropy thermodynamics optimized with respect to escort weight linear energy constraints. And here are these distributions which can be transformed all to one. Okay, and now put simply what is the idea with the mapping H, and I like always to use this figure. This is like yes, Archimedes, of course, and this famous sentence: "Give me a lever long enough and fulcrum on which to place it, and I shall move the world." And here I felt free to rephrase this great sentence, and I put give me a good pseudo-additivity rule and equilibrium distribution on which to place it, and I shall move non-extensivity to extensivity. The point is that we are given in a certain system, we are given probability distribution, and we want to know what is thermodynamics behind it. If we try with Boltzmann-Gibbs first, if it is Boltzmann-Gibbs distribution, we can try with Boltzmann-Gibbs thermodynamics, but it might happen that it is not extensive, and then it cannot be used to make thermodynamical predictions. Then we can move to another kind of thermodynamics which produces the same distribution, Boltzmann-Gibbs distribution, or we can also think if we are given Q Gaussian distribution is a stationary distribution of the system, which is confirmed in several types of system that holds. We can think about Rene entropy and its transformations, appropriate transformation, which will produce an extensive thermodynamics. Before I move to information theory considerations, I would just like to make a short pause here to show you this interesting given. This is organized by me and a few of my great collaborators, Jan Korber and Shami Gupta. This is the conference which is chaired by George Kaniadakis and Antonio Scarfone, all great researchers from the field of generalized entropies. And for all of those who are interested more in these and related topics, so feel free to save the date. It was planned for 2020, now is moved for 2023. The link will be available around. Okay. So let us move now back to information theory. And let us see how to use these information measures in information theory. And there we do have a basic notion of information channel that is actually the probability distribution between x, random variable x, and random variable y. And x serves as a sender, y serves as a receiver. Then we want to measure how much of information is passed from x to y, and we would like to establish a measure of information transfer as well as a measure of maximal information transfer, which is called information capacity. And standard Shannon theory deals with information transfer measures which are based on Shannon entropy. And here we saw several interesting classes, several interesting possibilities with generalized entropies. We are now interested in how to measure non-additive information transfer. And particularly in this case, we are considering Sharma-Mittal channel, Sharma-Mittal information content, and we aim to define Sharma-Mittal information transfer measures. Again, we would like to set up a kind of axiomatic system, which will give us clear insight into the properties that we ask from the information measure. And to do this, let us first take a look to some toy channel models that will help us to understand what do we want actually from the information measure. And here are two simple channel models. On the left side, I put binary symmetric channel, maybe the most common information model in theoretical considerations. And so on the left side, we have X as a sender, right side Y as a receiver. X can send X1 or X2, and Y receives Y1, Y2. If X1 is sent, Y1 will be received with the probability 1 minus P, Y2 with the probability P, and the same for X2. If this parameter P is equal to 1.5, then the output distribution will be uniform regardless the distribution of the input. And in this case, we will not be able to recover at all the input. This is one limit case. On the other hand, if we put this P to be 0, X1 will be always mapped to Y1, and X2 will be always mapped to Y2. So in this case, we have perfect transmission. And this binary symmetric channel actually goes between perfect channel and fully destructive channel. And we ask from our information measure that in perfect channel, it describes that the whole information is transferred from the input, and in fully destructive channel, we ask that there is no information transfer to the channel. And here on the left side, I put this requirement for this fully destructive case. So in this case, we have 0. On the right hand side, I gave one more example of a channel which is noisy channel with non-overlapping outputs as a simple example of a channel which can do the perfect transmission. So although X1 can be mapped to different Ys and X2 can be mapped to different Ys, the set of these Ys are do not overlap. And once we receive some y, for example, we receive y1, we know that x1 is sent. If we receive y2k, we know that x2 is sent. So we are always able to recover the information from the input. And in this case, we ask from our measure that it information transfer measure to have the value of the input information. And this is the second requirement. And yes, here we put in this axiom A2 and A3, we put these two requirements. The axiom A1 asks from our Sharma-Mittal information transfer measure to reduce to standard Shannon case when the parameters are going in the same way as for Sharma-Mittal reducing Sharma-Mittal entropy reducing Shannon entropy case. And we also add here few more requirements which are more about physicality of the information measure we aim to develop. And this asks first that our information transfer measure is non-negative. So if we measure the information, we expect that it is a positive number. Then we expect from information transfer measure to be upper bounded by maximal possible information that can be generated by input and the maximal possible information that can be received by the output. Because if we say that information transferred more information than it was sent, it means that channel added additional information without reason. And similar consideration can be done in the case that information transfer is higher than the maximal output information. And from these requirements, okay, we called it axioms, we now try to find suitable information of Sharma-Mittal information transfer. So first we recall Shannon information transfer, which is defined from Shannon conditional entropy and Kyle divergence. And Shannon mutual information can equivalently be defined in one of these ways. And of course, Shannon information transfer measure satisfies all aforementioned axioms. Now, the next step in choosing the measure will be to go to the next generalization. So if we remember this map, it was Shannon is generalized by Rini, and then Rini is generalized by Sharma-Mittal entropy. So let us do the first step from Shannon to Rini. And if we try to do this the same with Rini entropy, we will come into the problem because generalization of Kyle divergence, which is Rini divergence, does not have so nice properties as Shannon one. Some properties are lost because of the generalization. And then I put here in the blue some non-equalities which are satisfied in Shannon case, but in this case here are not satisfied. And then I apologize. And then the question is, what is the right definition that we can choose? And by inspection, we came to the conclusion that only the first definition could be used as a measure of information transfer. So now we do have we can also interpret this as a difference between information at the input and the information at the output, the information at the input if the output is given. Okay, Sharma-Mittal information transfer will follow straightforwardly by replacing corresponding information measures with Sharma-Mittal information measures, and here are some graphs showing the behavior of Sharma-Mittal capacity, which is maximal Sharma-Mittal information transfer. What can we observe here? Let us go to the left graph. In the case of P equals 0.5, which is the case of fully destructive channel, we have zero capacity, which means that we do not transfer information to the channel. In the case of P equals 0, we do have the channel capacity which is equal to the maximal input information, which is log Q in the case of Sharma-Mittal information measures. And between these two cases, we will have the range of possible behavior of Sharma-Mittal capacity. Okay, so here I would just like to point out some final remarks, some points that I aim to mention, but it was not time to consider all of these. I mentioned these Schur-Johnson axioms. They are established for this strongly pseudo-additive entropy class. They put very nice connection between information theory and statistical inference through this maximum entropy procedure. What is here still unknown, how do they relate to another kind of information measures which cover this Kaniadakis Sharma-Mittal Tanea class. It was the right side of the map. Future questions that were not considered here about relationships with the role of this axiomatic system in quantification of information measures, like interaction, information, redundancy, synergy, multivariate interaction, and so on. And also an open question about further roles of generalized information measures in causality modeling, information processing, and thermodynamics. So I would like to thank you for your attention, and of course, I'm open for the questions.
Thank you very much. Before we go to questions, let's thank Velimir with a round of applause.
Thank you.
And yes, we can go ahead with questions. Yes, please go ahead, Peter.
Thank you for your nice survey. At the beginning, you mentioned that the various definitions you had on that table originated in part from mathematicians and in part from people doing generalized thermodynamics in physics. Are there any contributions from computer science?
Computer science, Well, there were in computer science, when we are talking about information, this is usually from the point of this algorithmic information, and in this setup, I'm not aware about a lot of attempts, a lot of successful attempts in the definitional application of this information measures as a measure of information. On the other hand, if we go think about computer science, which applied computer science, for example, machine learning, yes, there are some applications, a lot of applications which are mostly based on using different divergence measures and also different entropy measures. So I'm not sure is this the answer to the question?
Yes, it's good enough for the time being. Let's get to another point. One of the crucial targets in using information theory in computer science is to try to discriminate between useful information and noise. There is an entire classical approach going already back to the time of Kolmogorov with all sorts of structural functions. Now my question is, these generalizations, do they contribute to solving that problem?
If you want to distinguish between useful information and noise, this is actually what in certain sense this capacity measure do. Also, the important point when we are going to distinguish between useful information and the noise is the role of the coding in information theory. And from the point of coding, we have well-established connections in Shannon setup, but also in Renyi setup. So we have very established connections between coding theory and information theory for additive information measures, which corresponds to mostly to memberless and IID sources. In the case of pseudo-additive measures, there is not a lot of work and not a lot of connections, and it is an open question.
Good, thanks a lot. I'll leave it to the others.
Yeah, thank you.
Yes, I see Clelia has a question. Please go ahead.
Yeah, so I was wondering, actually it's related to the last question. I was wondering in the case where you want to analyze some data and you want, for example, to use maximum entropy principle, maximum entropy model for analyzing this data. How do you know, how can you know what is the correct measure of entropy to use for a specific type of data? Like depending on I don't know, some known properties of the data, how do you know which measure of entropy would be appropriate for that specific type of data set?
This is a bit tricky question. First, when we are modeling data, the first notion that we will meet is the maximum entropy distribution, which fits our data, and then after that, maybe we will not need at all any kind of entropy if we are given the maximum entropy distribution and we know how to determine it. If we do need entropy for some reason, then it will depend on, in accordance to the discussion from this presentation, in another context, maybe another answer could be more appropriate, but I'm talking from the point of view of this presentation. If we want to conclude what is the entropy measure, which is the correct one, we will need to go to asymptotic analysis, which means that the number of data tends to infinity, and that we want that our measure have nice behavior in this case as well. So we actually, with this, okay, let me show. Okay, maybe this graph might be good. And this one. Okay, let us see this one. So this is, I'm showing the first line, R alpha UL thermostatistics, and this is so-called Q Gaussian distribution. And in the case of alpha equals 1, it will reduce to standard exponential. And we are given data. They can fit standard Boltzmann-Gibbs distribution, or standard Boltzmann-Gibbs distribution is not appropriate. They will fit another distribution for another alpha. And then in this, using this data, we will determine the parameter alpha. And we are now, we have fixed distribution. But now we go back to this slide. We are interested what is the right choice of this function h, mapping from R to h. So any of this any choice of function h will lead us to the same distribution. And to determine the right one, the right choice of h, we will need to take a look to asymptotics of the data.
Okay, thanks. Thank you, sir.
Okay, if there are no further questions, let me just take a look. Then we can thank Velimir again. And we'll see you next time.
Yeah, thank you all. It was my great.
Janus, I think there is a question in the chat.
Yeah.
I see Jay has a question. Is there another physical notion of entropy that is still yet to be written down?
Another physical notion of entropy still yet to be written. I think there is a lot. I think there is a lot. Depending, so again, it depends on what is a stationary distribution. Here I touched just this so-called power law stationary distributions of this form. I touched this form distributions. Stationary distribution can be something else. Then we will need to search for another measure of entropy, and also what is the asymptotic behavior of the system given by the system Hamiltonian, and then we will also need to fix this pseudo-additivity. I think that there might be a lot of new measures that could be written down.
All right, thanks.
Can I also ask a quick question?
Yes.
I was wondering, so for example, for Shannon entropy and generalized Rayleigh entropies, we know that as mathematical functions, these are convex functions. Do we know similar properties about other notions of entropy that you talked about? I mean, these would become important, for example, when we want to maximize entropy or minimize relative entropy, then the convexity would give us uniqueness in many cases. I was wondering if we know this type of mathematical properties about the other notions of entropy that you talked about.
Yeah, this is actually, we know for Rayleigh entropy we have another kind of property which is like Schur concavity, and this is a kind of generalization of ordinary concavity, because it is not mandatory for a function to be concave so that it has maximum. And this is usually the case with Rene entropy. It is not neither convex or concave, but it has unique maximum for certain range of parameters with both constraints and without constraints. This is one. Then if you take increasing transformation of such a function, then it will be the same. We will be able to maximize, but it is important to have unique maximum in all of these considerations. And also one interesting notion related to this that I haven't mentioned, exactly on this slide, when you go to this blue formulas, and when you go to this, this is how each of these equations is one attempt to define Rene mutual information. And then the question is, why do we use at all these complicated equations? And this is exactly to ensure concavity with respect to one of the parameters. Is it the channel or the input distribution or so on? So this is, but it is not so straightforward as in channel case. Once we move the parameter alpha, it becomes a bit more complicated.
Thank you very much.
Okay, now it seems like all the questions have been asked. So thanks very much for attending, and we'll see you next time.